He is a PhD student at the Department of Computer Science, the University of Freiburg, and I'll pass it off to him. Thank you so much.
Cool. So I hope the slides are shared appropriately. Can you see it?
Yes, we can.
Okay, good. Thanks. So I will start. This talk is about the discipline biconvex programming. I mean, it belongs to one of the discipline families, right? So the overview, sort of the overview would be, the following. So WEL is a domain-specific language for biconvex programming. I will define how biconvex programming is formulated later. But this WEL is a Python package as an extension of CVXPY. And for the solution, I should say that it's a heuristic based on alternate minimization. There are some theories which were not done by me. I mean, many years ago, I think some of them even trace back to sort of 100 years ago. But there's a good review paper here. Well, the major application of this package would be prototyping of many machine learning problems like clustering, especially with constraints and regularizations. And another class would be sort of generalized principal component analysis, which is basically some sort of matrix factorization. Well, of course, you can add in some non-negativity constraints or orthogonality constraints. I will introduce some examples later. But I personally think, and many of my colleagues think, the most useful cases would be fitting latent factor models. And one of the most famous one would be the hidden markov models with different observation structures. Right. So the general idea would be, many these machine learning problems used in scientific computation can be formulated as a biconvex program. Although we cannot solve it to global optimality, but in general, alternate minimization gives quite good point that that is good enough in most applications. So that's the idea. So I will briefly just run into some theories, like what a biconvex set is in general. Intuitively, it just says, the set consists of two groups of variables. If you fix one of them, then the other one is convex. And some basic examples in R2 would be like these T-shaped, L-shaped sets. This is a specific example showing that a biconvex set could be unconnected. And from this, you may notice these problems, involving biconvex sets can be very hard, right? And one of the most important property, right, intersection of any number of biconvex sets is biconvex. Well, this is just conceptually good for recognizing different biconvex problems. And again, we have similar definition for biconvex functions, which says, if a function consists of two groups of variables, and if we fix one group of them and the other one is convex, right? So that's just what this says. And we can similarly define the biconcave, bi-affine, and bilinear functions in a similar way. Some analysis properties like sublevel sets. If it's a biconvex function, then any sublevel set is biconvex. And some operations that preserve biconvexity. This is almost the same as convex functions, right? We have non-negative weighted sum, pointwise maximum, supremum, and there's a little bit of variations here. It's just the bi-affine precomposition, which says if H is convex, then a bi-affine precomposition of H is biconvex, right? So I based on my experience, I think that's one of the most frequently appeared form in biconvex optimization problems. And many famous problems like matrix factorization, if it's biconvex, then it comes from this form. These just two examples. One, this is bi-affine, and this is a function, this is sublevel set, and this is a product of two quadratic, which is biconvex, of course. Okay, then based on these, we can have this definition of biconvex optimization problems, well, it's similar to convex optimization problems, and the difference is that the objective F0 and the inequality constraint functions are biconvex, and the equality constraints are bi Fi, right? So if you're familiar with convex optimization problems, then biconvex optimization problems are more or less similar to that. And again, you may notice, so this is biconvex set, and you can show this is also biconvex set. So an abstract form of biconvex optimization problem would be minimizing some biconvex objective subject to a biconvex set. And I think many theories, right, analysis are based on this abstract form. But in practice, I think this form is more useful to specified problems or something like this. Okay, and regarding the solution optimality, since, as I said, mostly this is NP-hard, and these also include many famous NP-hard problems like k-means clustering. So normally what people search for is a partial optimal point, which says, well, if you fix one of the variables, then the other one is optimal, right? And vice versa. So this is somehow equivalent to, well, under some technical conditions, this is equivalent to stationary point, right? And from this, you may know that partially optimal point is not necessarily a global optimal or even locally optimal, since it can also include set of points. There are several basic examples over there. And in the end, well, although this is no optimality guarantee, but in practical applications, this solution, approximate solution, of course, turns out to work quite well. And so most people just focus on, and of course, including us, focus on finding a stationary point, which is according to this alternate convex search procedure, right? And also, if you look at a biconvex optimization problem long enough, then you will recognize, well, of course, you can fix one of them, and the rest problem is convex, so that you can use any convex optimization solvers to solve that, right? And you iterate between solving the two, solving with respect to the two group of variables, then you finally converge, right? There's not much we can say about the convergence, but one thing we could say is that based on this method, we can find a stationary point, which is hence, well, partially optimal. And this is just a snippet of a minimum algorithm. I mean, there are some variations in practice. For example, you can add proximal regularizations in the objective so that each subproblem is strongly convex, which has better numerical property or something like this. And you can have penalty methods for infeasible start. But I will not go into details. This, just there are some variations over there. Okay, then how we integrate this into the CVXPY, which, based on what I've said about the properties of convex functions, we can inherit almost all the rules from DCP, the discipline convex programming. And the two extensions we have is, the product rule, which is the following. So in general, a product of two expressions involving variables is not as, we cannot say if it's convex, concave, or something. But for well, a biconvex problem, if we have if it's one of these, then it's guaranteed to be biconvex. For example, if we have Fi, Fi, then this is bi Fi, right? So which is hence convex, biconvex. So one exception I want to say here is that, well, although we allow a product, but no loop is allowed, because if you look at it, you cannot separate these variables x, y, and z into two groups where you fix one of them and the other one is convex. But this is indeed a multi-convex problem, and there are, I mean, I believe there's a CVXPY extension for that over there. Okay. Now I will just say about some simple examples, right? As I said, the principal component analysis. Well, maybe this is not the most familiar form that people know, but in the end, it's just like this, right? There is an implicit rank constraint on x and y, here, right? since, well, this is defined based on by the dimension of the matrix, right? And we can add in many extensions. For example, we can have quadratic regularization, right? We can have non-negativity constraints or orthogonality constraints. Well, in the end, these problems are just biconvex. So, with this package, we don't have to. Well, of course, for these form, we have a closed form solution based on singular value decomposition. But if we have constraints, it's not necessarily the case. And with DBCP, we can specify the problem in a way that people can fast prototyping, right? If play with the components of a problem, right? So that's the idea. And we have the same for k-means clustering. So I would just briefly parse that. So this is, xi are the data point that we want to cluster, and these x bar are the variables, which is the cluster center that we want to find. So these factors specifies the distance of each sample to the cluster center. And this z, well, here you can see this is sort of a probabilistic probability distribution in a simplex, right? So it can be considered as a soft cluster label. And then we have this inner product, which gives us the expected distance, right? Sort of mimic the distance within clusters. And we minimize that, and we find both, we try to find both z and x bar. So we have the solution of the k-means clustering. And of course, there are, if we just look at that, there are many solution methods for that. For example, I think Linners, I can't remember, but there are some algorithm for that. In the end, if you have some constraints or organizations, the solution is not obvious, although we can still implement that in Python, for example, in 15 lines of code, right? But you can notice if we specify this with that, this is just 4 lines, and you can possibly add in constraints here, just 1, 2 lines of code, so that you can call problem.solve, and then you have potentially a good solution for that. And the only difference between these code snippets and the CVXPY would be here is a Biconvex problem instead of a CP dot problem. So that's the idea. Okay, so I will quickly go into sort of the example that some of my colleagues are using as in much more detail. So it's called input-output hidden Markov model. So maybe what hidden Markov model is. In the end, it's like we have a sequence of hidden states, say that's Z, right? It's from Markov chain, and this Markov chain has initial state distribution and also the transition matrix. Then it's a generalized hidden Markov model in the sense that the response Y are generated from a logistic model, which is given by this probability, right? And the X are the features, and this theta here are, belongs to one of these K thetas, which assigns the different coefficient to different state of the Markov chain. So, and I should say this logistic model is not the only way of extending hidden Markov models that result in a biconvex model fitting problem. This is one, many people use that for the modeling of the decision-making behavior of rodents, for example, rats, animals, humans, and they have kind of wide usage in psychology, neuroscience, stuff like that. Then, okay. So for the fitting problem, we want to search for the transition matrix and the parameters. So what we do is the following. So instead of directly modeling the transition matrix, which is the Baum-Welsh algorithm does, right? What we do is first learn or estimate these hidden state probability as similarly to what we did for the k-means clustering. And then the objective would be the negative log likelihood of the observed data. And this part is just the log likelihood under a logistic model, right? if you're familiar with that, you can recognize it easily. And then we have this part, right? This again, as in the k-means, this is just expectation based on the soft label of the hidden states. And then this is biconvex in Z and theta. And in particular, since this logistic regression objective is convex, well, concave, right? If you take negative, then it's convex. And then if you, for example, if you fix Z, then this is just the ordinary logistic regression based on some random, fixed label, stuff like that. And if you fix the theta here, this is just, well, linear affine objective. So this is biconvex. Okay, so if we stop here and try to find a solver for these objective, this is quite easy, right? You can easily extend the bound voyage algorithm, expectation maximization stuff. Maybe you can implement that within 50 lines of code. Well, this is good, but in practice, many people in those neuroscience psychology field, they also consider some prior information, right? There are several. The most widely used would be that the coefficient should be small, right? And the hidden state transition should be sparse. For example, the transition matrix close to identity. And potentially there are some constraints on coefficients like non-negativity, monotonicity, things like that. Okay, so how those people I know deal with this prior information is that they just ignore it and build the model based on whatever bound voyage algorithm or something like this, and they start to tune the random seed, right? They sit there for half an hour or something. They tune different random seed, and until they find one that satisfies these prior information, right? They check the result every time they have a random seed, and at this time when they found one good random seed, then they write it in a code and push it to GitHub or something like this, right? And tell people not to change it anymore. But in theory, we can integrate this information directly into the optimization problem so that we can force that somehow in a way. So this is the biconvex problem formulation. So this is the objective, and this is a Tikhonov regularization we add to the coefficient, right? So to make it small somehow, right? And then this part is based on the KL divergence, right? Since it measures the difference between the two probability distributions, and since this is non-negative, then we just add them up. It's just or equivalently to applying AL1 heuristic to sparsity, right? So this means that we force the state transition to be sparse. Okay, and then we have potentially have some constraints on the coefficients, and now people can formulate these problem, or people can type this problem in DBCP and then cause off with different hyperparameters, right? And until a point they find a good solution. And I'm not saying that people don't have to tune the random seed here, right? Since it's again non-convex, but could potentially make this time significantly shorter than just ignoring these assumptions. And you will see this in example. So this is the example. What we have here for the transition matrix, the ground truth would be something like this. You can notice there is a large entry in the diagonal. And also we have some constraints here. Oh, I should say these sort of constraints maybe look a little bit random, come out of nowhere, but actually it's not. Because as one example would be people wants to fit the model to different data sets. So when people fit to the first one, they have some estimation of the coefficients, right? Well, maybe this time they don't have any constraints, but if they want to fit the model again to the second data set and they want to compare between them, they kind of want alignment of the coefficients. So for example, they want the first one to be non-negative, the second one to be non-positive, so that they don't have to swap the coefficients after they solve the problem, right? So that's probably where these constraints coming from. Okay, so that's the code for specifying the problem. And you may notice this is quite short, 10 lines somehow. And I don't know if you have tried to implement the expectation maximization for a hidden Markov model. It's like at least 10 lines or 20, 30, right? In the end, this is just 10 lines plus a problem.solve. So people can use that to prototype their models. And to be honest, for these models, people really need to prototype it based on their applications. So this would be quite useful for these application scenarios. Okay, so this is final result by calling problem.solve based on this code, right? And you may notice there are some, for example, here there are piecewise constant region of the state distribution. Well, this is just an example, right? There are, well, if you find in the literature, there are many applications of these models there, and they all require these property in a state distribution. Okay, so I will finalize listing some resources. The paper is now currently on archive, so that many people can read that and use that. And the package is on GitHub, and you can just install that with pip, right? There are also some examples in the repository. Mostly are based on what I have said, for example, clustering, dictionary learning, stuff like these, but we're welcome to other applications. So okay. And I will stop here for the talk. I don't know if you have time for questions, but I will be happy to answer if there are some. Thanks.
Thank you so much for that fantastic talk. Let me check the schedule. We have 1 minute left. So if there's one question, we'll bring the microphone over. Mic working? It is. Okay, we'll use this one next time.
Sorry, can you generalize this to multi-convex programming by convex constraint and lift it to a higher space and put in the biconvex constraints, and now we'll do multi-convex with just kind of minimal changes on your end to implement the lifting?
Yeah. So I think the question would be about generalizing to multi-convex set. And actually, I think there was a package extension for CVXPY for multi-convex problems. And I don't know, for some reason it's not maintained, but in theory, we can. And well, as we said, there's not, just basic update of the solver, but potentially the question would be how the numerical stability. That's the only thing I'm concerned. But in theory, this is feasible. We can extend that to multi-convex setup.
Thank you so much.
Thanks.